Berhampur, since 2017. And his broad research area is mathematical aspects of quantum information and matrix analysis, which includes quantum information and computation, matrix analysis and application, information theory, and quantum probability. And today we'll be talking about conditions of LOCC transformations between sets of quantum states.
Okay.
So I welcome Dr. Sengupta to present his talk. It is for 1 hour, including question and answer. So Dr. Sengupta, please.
Sure, I think I'll take much less time than that. Thank you, Utpal. But just give me a few minutes to upload my slides, just or to change my system. I don't know. I mean, just let me see how I can share. How can I share?
You can go to
share content. Yeah,
and buy, yeah.
Clean. Just a second. Share content. So I can just see in the start broadcast. And okay. So can you see my screen now?
Your screen is visible.
Please let me know.
And your sound is also okay. You can go ahead now. Yeah.
Okay, fine. Okay. So I'll not take 1 hour. I'll take much more shorter time than that. So thanks a lot for calling so that I can give a talk here. It was very nice 2 years, 3 years ago right now in 2019 when this whole series started. And I wish that someday we will again meet at IISER Calcutta for this occasion. Anyway, so for now, let me start giving the talk. And this one, because I have a lot of time, I just try to give some kind of, some kind of an understanding about what the problem is actually. And this problem, this is the title of the paper, that LOCC conditions of LOCC transformation within a set of quantum states. This is a recent paper with Somsubhro Bandopadhyay and Saronath Halder. Let me first tell what we wanted to do and what is the motivation for this kind of things. So this problem actually, hello. Oh, I think I have to then just give me a minute. I think, yeah. So has it been moved now, or has it been moved now? Yeah, perfect. Okay, thank you. Yeah. So so this story actually goes a little. This is quite long ago, and before the state transformation problem. So what is a state transformation problem actually? This problem started with a little different way, and naturally it started with from the probability theory or classical statistics, where the problem was something like the following. So you were given two probability distributions, and you were told to distinguish between these two probability distributions. Very standard question. And how to do that thing? Well, this is the classical hypothesis testing, and which was been asked by the Shannon Blackwell, and there is a very, very famous results are there. Then there are this multiple hypothesis testing and so on and so forth. Okay. So this is in the classical side. Now about the quantum side. So how do I do it in the quantum situation? Remember, what we do is the following for quantum probability settings of quantum mechanics is that what we do is we try to take, we replace those probability distributions by density functions. Okay. So we have the probability distribution F is replaced by a positive semi-definite Hermitian operator rho. We are doing everything in the finite dimension. Naturally, it can be done in infinite dimension also, but I'm not bothered right now. So now I can ask this kind of question that suppose I have given a set of input states, rho 1, rho 2, etc., rho n, and I have a set of, sorry, there is a small mistake here, rho n it should be, and there is a set of output states, so sigma 1, sigma 2, etc., sigma n. The question is that how we can how to have a transformations which sends this rho I to sigma. Okay, Now, this, how do we do the transformation? Well, in quantum mechanics, when we call about a transformation, this transformation must be a quantum channel, which means I need to take a completely positive trace preserving map, and this trace preserving map will be of the following form, that phi of rho j will be sigma j for all this j is equal to 1 to n. Okay. So this is my task. And this task is, of course, I can call it, I have a different name for this problem also. This is something which I can call it like quantum interpolation problem. Though those who know this term, they know that this interpolation problem goes slightly different way in Banach space, but this is also a type of interpolation problem in this following sense, that see, in standard interpolation problem, what you are given is a set x is a set of points x1, x2, xn, and another set of output points y1, y2, yn, and your task is there to fit a some kind of a curve between those points, which passes through those points, that is xi goes to yi, but also that is in some way the minimal and all that nice things. And typically in interpolation theory, you try to define this kind of map by using a polynomial function, or if you are a little more smart, then and if your situation requires it, you try to use it trigonometric functions. So this is how the standard interpolation theory works out. But we are in quantum mechanics domain. So when I say that I need to have a map, so then all natural maps which takes place in the quantum theory has to be a quantum channel. So I am asking the same kind of set of questions. I have some pairs, rho I, sigma I, and can I have a quantum channel which sends the object to phi of rho I to sigma. Okay. Now, okay, so far so good. What is the simplest way to do that thing? Those who are a little bit of mathematically minded, they can just quit very easily. That, well, you know, you can consider a sister algebra spanned by those rows along with the identity, and then you take another sister algebra spanned by those sigmas, and then you consider this send the rho I to sigma I. That will be definitely a completely positive map. It will be also trace preserving also. Then you take the span of that thing, so it will again be a completely positive map. And we have to stop exactly there, because then the next step, which is very natural, is to say that you extend the whole thing to the whole sister algebra, which is your D of H. But we know that only one thing here, that I can extend this thing by using a positive map. I cannot say anything about completely positive or completely much less on the completely positive trace preserving map. So this is what is called as the Arvidsson extension theorem, and Arvidsson extension theorem stops before completely positive itself. So we need to do some work, and there is a scope of research on that. And the first, this whole thing was approached by Alberti and Ullmann in this year 1980 in the following paper, and they considered the very simple situation which we now know as the qubit system. They had this qubit spaces to qubit spaces, and they had just only two systems. So rho one, two states, rho one, rho two, and they had two output states, sigma one, sigma two. The question is that, can we find out a completely positive trace preserving map, which we now call as channel, such that rho one goes to rho sigma one, rho two goes to sigma two? And the answer, they showed that such a channel exists if and only if for each t positive, I have this nice relationship between this nice inequality holds for each t greater than 0. Okay, so this is an if and only if condition. And this is not a very simple condition. They had to actually work really hard to get this condition, if you see the paper. And naturally, what they found out was that this may not be possible to extend in arbitrary dimension, probably not as an if and only if condition, but something probably can be done. And indeed, Alberti actually, sorry, not Alberti, Ullman actually worked it out by using fidelity function, that if we call this sets, the first set as set of S rho and the output state as S sigma, then the fidelities of the outputs has to be greater than equal to the fidelity of the inputs, and this is a necessary condition. If this transformation holds, then this happens. But the converse actually is not completely true. I mean, you need some conditions which we are not yet been able to figure out. So these are the two things which comes very close to our area. And mind it, at that time they didn't use the word qubit and all that, which we are very comfortable right now. And so they just call it as a state in the C2 and so on and so forth. Okay, but from the quantum information theory side, of course, there are a couple of people like Cliffs and Andreas Winter, and Jose also was there in these papers, where they actually worked out and found out, just strengthen this condition a little bit more, and this condition a little bit more for arbitrary number of particles in qubit systems, but they couldn't go much beyond that. Okay, so this is on the physics side. Now a little bit more on the mathematics side. So so there was so mathematicians also were involved in that thing. Some people, of course, were from the quantum probability side, looked at this problem for quite some time and made some progresses. But one interesting progress, though it is a very small, it was done by Lee and Poon in this year, in 2011, this linear and multilinear algebra. They found out a set of necessary and sufficient conditions. But for that, they had to do a lot of compromise. They assumed that these rhos and sigmas are commutative, which means, you are assuming too many things. After all, then you can, if they're commutative, then you can just simultaneously diagonalize all of the things, and then practically, instead of everything, you can just take the rhos as some diagonal matrix and sigmas as some diagonal matrix, and then you can ask the question that whether there is a completely positive trace preserving map which sends a diagonal matrix to the diagonal matrix, which is pretty simple if you can work it out yourself, actually. So there are some nice conditions you can get it, and of course then you put the u and u dagger in the other, u in one side, u dagger in the other side, and then life becomes easier. But then naturally you understand that life is not so simple. But what is interesting is that this technique can be extended to a great extent. Actually, it's surprising that even if they're for non-commutative tuples also, this something can be done. And there are quite a lot of papers on that, very, very powerful papers, but they are on some sister algebra operator spaces and on the certain norm classes operators and so on and so forth, which I don't need to go in that direction, so I didn't put here. But important thing is that paper by Davidson and Benor, Salath, and Davids, these four very powerful mathematicians, which came in International Mathematical Research Notice in just a few years ago, 2016, where they showed that this thing is possible provided their matrix ranges coincide. Actually, in fact, later they showed that actually this is the other way is also holds. It is an if and only if condition if the joint matrix range is of the output states is sitting inside the joint matrix range of the input states. Here also, because I want to quickly go into the physics side, I don't want to spend too much time on these matrix ranges. Rather, I want to say a little bit more by a work of Bode, Buscemi, and some other fellows which came in Nature Communications in 2018, where they showed that such a thing is possible, that the existence of such a map or a channel is equivalent to several other questions about thermodynamics, and you can find out some very nice conditions about the minimum entropy of those of the joint states, actually. So the trick they had used is the following: with each rho I, they put a pointer states, and they consider the states something called as the summation of theta bri tensor with rho I, and take the summation over all those i's. Similarly, they did for the sigmas, and then they considered the following thing: that is it possible to have a mapping such that identity is that one tensor, that mapping sends this big classical quantum state to that other classical quantum state, and then they showed all these nice relationships between them. This is a very, very beautiful paper. You can actually work out if you read the paper, and then finally they showed that everything follows from some positives from some STP problem actually. Okay, now what we want to do, if this much is done, then why we look for this LOCC thing? See, if LOCC has some very, very beautiful and some very bizarre structure, because you see, it may happen that you can have two pure states or a set of pure states which are orthogonal, but you cannot distinguish them by using LOCC. So this kind of bizarre situations may happen. Similarly, you can, for more practical purpose, you can actually ask this question that, can you, let's say a set of states, can you distinguish them? Well, of course you can distinguish them, and there are some nice results on that, but can you do it by LOCC? There this problem starts actually, because many of these things will not work if you don't allow entanglement. LOCC is something very, very interesting in that respect. So we ask the same question, that can we do this conversion by S from S rho to S sigma by using LOCC only? Okay. Now, for LOCC, we have to do some basic assumptions. So my assumption is that the input and output systems are same. That is something like HA tensor HP. They are bipartite also, and they're and as I mentioned, that there are situations in which this states, input and output states, cannot be distinguished by LOCC. So it gives me again another layer of uncertainty and trouble for our work. So now we need to actually find out some conditions which holds for LOCC. Okay. So let us see. Now, the first condition which comes in our mind is actually quite old. It is by Nelson, that measurization condition. So if you have two bipartite states and chi and psi, and then which have been coefficients are given by some alpha i's and beta j's, where these coefficients are written in the increasing order, then there is a deterministic LOCC to transform from one state to the other, first state to the second, if they are measurized actually. That is, the summation I is equal to 1 to L, alpha I square is less than equal to summation I is equal to 1 to L, beta I square, for all L from 1 to up to minimum of the number of this coefficients, M and N. Okay, so this is the first condition, which if I just give an input pure state and then output pure state, can we have an LOCC? So this is the very first condition which will come in our mind, and it will be always our first condition here. So let us see. Now, if we have this kind of situation, then first, obviously, if I have this pure state psi1, psi2, psi-n, and I have another pure state output, that is which I say as S of psi is phi1, phi2, phi-n, for each pair psi-i, phi-i, this Nelson's criteria must be satisfied. So this is a necessary condition, definitely. Next, I have been given a set. Now I can consider the probability distribution also, and I can make an ensemble of those states like psi1, psi2, psi-n. So let us call that at the row of psi1, row of summation of pi, psi1, ket psi-i, bra psi-i. Okay. So that will be a mixed state naturally with respect to some probability distribution. And similarly, you define this with the same probability distribution for the output state also. Now I have only one mixed state row, and I have another P output state row 5. Now the question is that, can we have a LOCC transformation? what we know from the LOCC transformation? We know that LOCC transformation holds provided if it holds, then if the states are entangled, then the entanglement measure cannot increase. Okay, take some entanglement measure, it shouldn't increase. Okay, so this is a nice thing. So this should be again another of my necessary condition. Then the third thing is a little bit more subtle. That is if you consider in the same way, the distinguishability of these sets S sigma, S psi, and S phi with some probability distribution associated with it, then this object, this distinguishability thing the output state shouldn't be more distinguishable. They should be less distinguishable than the input states. So this is my third necessary condition which I can figure out. Now, I want to show next in another half an hour that all these conditions are necessary and I cannot merge any of these two conditions to a single one, and they are not sufficient also. Okay, so okay, right. So now first thing, so let us see, recall that what we found out. I say that Nelson's theorem is A, entanglement criteria is B, that entanglement measure will not, measure of entanglement will not increase, and distinguishability measure is C. Now the next thing, just a second. Okay, A holds, B and C do not. That means the entanglement amount of entanglement the Nelson's criteria holds, but the entanglement with respect to entanglement measure, it doesn't work out, and with respect to the distinguishability measure also, it doesn't work out. By the way, the previous, I have not proved the previous theorem, but it is actually very easy to see because the first one is obvious. The second one is also obvious because it follows from the Nelson that again it follows from the Nelson that entanglement measure should not increase under any nice entanglement measure shouldn't increase under LOCC, and the third one also is follows in a very similar manner. So I don't really need to prove that thing. It is actually follows from the fact that the distinguishability of a given set of states cannot increase under this LOCC transformation. So the ensemble cannot be cannot be less distinguishable than the output ensemble for any probability distribution P. Okay, so this is the. Now let me try to give these examples that I have the situations in which the first condition holds, but the second and third condition, that is the Nelson's condition holds, but entanglement measure and distinguishability measure it doesn't hold. So this is my set. This is my choice that psi 1, psi and phi 1 are like this. Now for the very first thing you see, the Nelson's criteria holds here, so there is nothing actually to prove for the. It's straightforward to check. The psi 2 also for the Nelson's criteria holds, and psi 3 also the Nelson's. It is after all it's a separable state, so there is nothing actually to prove. So you can just do by using a LOCC. You can convert from one to other. Mind it, when I am saying that by LOCC you convert from psi 3 to phi 3 or psi 1 to phi 1. This LOCC which transfers from this to this may be quite different from which it does for the second one or the third one. What we are looking for is a combined LOCC which will do this transformation. Psi 1, psi 2, psi 1 goes to phi 1, psi 2 goes to phi 2, psi 3 goes to phi 3. Okay. Now, so first one is straightforward. Second one is also actually straightforward. So if you see, if you take an ensemble like this, that probability distributions, take some P which is between 0 to half, and then take a combination, the P 1 minus 2P. Then you define this row of psi comma P hat. That is, you recall it is P psi 1 psi 1 brush psi 1 plus P ket psi 2 bra psi 2 plus 1 minus 2p into ket psi 3 bra psi 3. You can show that this all of them are separable for 0 less than p less than half, but the output thing, which you can again rho of psi comma p hat, is entangled for all those things between 4 by 9 to 1 by 2 p. This p, when is taking the value between these two things, it will be separable. It will be entangled. So that means the output state's entanglement is increasing. So naturally, I cannot do this kind of transformation. The third one is a little bit more subtle. Actually, this is a result by Walgett and Hardy, which tells the following, that 3 orthogonal 2-qubit pure states can be distinguished by LOCC if and only if at least 2 of these states are product states. Okay. So you see, this part is more distinguishable. It becomes, because it can be perfectly 2 of them are product states. So these 3 can be distinguished. Whereas in this side, only 1 of them is a product state. These 2 are the Bell states. So this guy cannot be distinguished. So in other words, the distinguishability actually increases this side, the output side. So this cannot hold. So so this is again another. This shows that the third condition doesn't work out. So this is one is the beauty or the mystery of LOCC, that you have these small results which are small but beautiful and creates a trouble for us, operationally a trouble for us if you want to do perform some kind of tasks. Okay. Now let's see the second one. That is the entanglement holds, but Nelson's criteria do not work out, and the distinguishability also. Okay. Now let us see. So Nelson's criteria do not work out. So condition A doesn't work out from the very first thing, because you see this guy is having the what is that called, Smith rank 2, whereas this guy's side it is having the Smith rank 3. So you cannot convert from one to the other. Naturally, the Nelson's criteria will not be satisfied. From here itself, you can work out. It's 2 minutes. There's algebra. This Nelson criteria will not be satisfied. So the condition A is not. Condition B. Condition B is that you can the entanglement measure it works out. This is a little bit subtle actually. So you consider a probability distribution with P1, P2, P3, and P4, and you take the E as the entanglement of formation. You see for the input states, all of them are separate, all of them are entangled actually. So if you mix them together, all of them are entangled, or you are mixing all of them together, what you will get is that you can show that there's entanglement of formation is at least. So then it is measured in C. You can consider the following LOCC protocol. So consider the situation that you have like 2 parties, Alice and Bob. Alice is having this 0 and 1 basis, and Bob is having this side 2 and 3 basis. Okay. Consider the first LOCC protocol. Alice performs a binary measurement that distinguish between the subspace, orthogonal subspace spanned by 0 and 1, and then 2 and 3. If she obtains the first outcome, she and Bob ends up sharing state psi 1. That's. And if she gets the second outcome, then they are in this part, and then in this part, psi 2, psi 3, psi 4. Okay. So the probability of getting this outcome of psi 1 is actually P1. So your entanglement of formation will be at least up to E1. For the second one, you see, for the second output side, you see the problem is the following. The phi 2, phi 3, and phi 4 are separable states. So their entanglement of formation is actually 0. So whatever will come up will be from the phi 1 side. So P1, get phi 1, bra phi 1. Okay. So entanglement of E of rho of psi comma P, phi comma P is it is actually less than equal to P1 of entanglement of formation from phi 1, because phi 2, phi 3, and phi 4 can actually, it may actually decrease the entanglement of formation. So it is less than equal to this thing. But again, a little bit of work for this pure state, which you can, because this is pure state, you can work out yourself, that entanglement of formation is less than P1. Okay. So, so because after all, the whole thing is entanglement, this E of phi 1 is actually less than 1. So by this thing, you can check that this entanglement of formation of this ensemble with that probability distribution is greater than the entanglement of formation for this. Okay. So the second condition, that condition B, is satisfied. Now again, condition C, that distinguishability is not satisfied. This is again a beautiful result by Bandopadhyay, Walgett, Nathaniel Johnston, and some others in 2015. It shows that this guy contains this, for this input states contains this phi 1, phi 2, phi 3. This subset is locally indistinguishable, whereas this phi 1, phi 2, phi 3, phi 4 is actually locally distinguishable. So if I take a local measurements, I can completely distinguish these guys, these output states, but I cannot completely distinguish these sites. So that proves that the condition C is not satisfied. Okay. Some more. The first two conditions are satisfied. A and B are satisfied. That is, entrance criteria is satisfied, as well as the entanglement measure is also satisfied, but not the distinguishability measure. This is rather actually easy, because this is rather actually easy. Oh, sorry, I made a small mistake actually. I made a mistake here, that this should be actually this side, and it became ulta. This is bad. So this should be actually 1 by square root of 2, 0, 0 plus 1, 1, and the output should have 0, 1. So I am sorry for this thing, but it can be easily seen by the previous arguments that the Nelson's criteria will be satisfied in that case. Mind it that actually phi 1 is phi 1 and phi 2 and phi 1 is actually phi 1. So Nelson's criteria will be satisfied. Measure of entanglement will also be satisfied, and it will be A and B. Sorry, my bad. So the distinguishability condition will be satisfied, but the Nelson's criteria and other two things will not be satisfied actually. Okay. Okay. Now, so this is a mistake when you try to when I was trying some last minute changes here and there. Okay. So in the same spirit, you can continue doing this. The most interesting thing I can say is that this typical case when this A and C are satisfied, but B is not satisfied actually. So in this case, you have to take this kind of input and output states, that phi 1 and phi 1, phi 1 is equal, phi 1, phi 2 are Bell states, and phi 1 and phi 2 are some alpha and betas are their real numbers, such that alpha square plus beta square is equal to 1. Okay. Now in these cases, if you see the first condition, Nelson's criteria is satisfied here, no problem. C is also satisfied due to the fact that the inputs are orthogonal states and hence they are distinguishable, whereas output states are non-orthogonal, so they are not distinguishable. Okay. Now this is a standard thing. Now the condition B is not satisfied, because you can see that for this probability distribution, if you take half of a mixture of both halves, then you see that this guy is separable, but this fellow is actually in that case it will be entangled. So the second condition would not be satisfied. Okay. So in the similar way, I can also continue with the other objects as well. This this B and C are satisfied, when A is not satisfied. All of them requires a bit of using a suitable entanglement measure and all that. And I can leave it as a small exercise for those who are listening and following. Now, is it possible to, so far I have just told that what are the things in which one is satisfied, other things are not satisfied, two of them are satisfied, one is not satisfied, and so on and so forth. Is it happen that all of them are satisfied? Well, that is the most easy thing possible. In that case, actually you can have the situation that you take three pure states, three states, I1, I2, I3, and then take some unitary, some local unitary operation, fixed local unitary operation U tensor V, and then define your output states as the unitary action on those things, on those input states. So they will always satisfy all these conditions trivially. So there are states which trivially satisfies all those conditions. Okay, so let me just all these things, whatever we have told so far, that if I consider this as A, B, and C, and then this A is the set of all those situations in which the first condition is satisfied, that is Nelson's criteria. SB is the case where this entanglement measure is that that condition is satisfied, and SC is the condition regarding distinguishability. Then they follow this kind of situations, and we have whatever we have shown right now is that all these things like this portion, like this portion, like this portion, these are all, if I can highlight this, and so on, all these portions are actually non-empty. That is what we have shown by using all these combinations so far. Okay, so this is interesting. That means we have situation, I cannot drop any of these conditions from the list. All of them has to be considered together. Okay, so all these conditions are necessary and it has to be satisfied. Now next is that they are not sufficient. This is very, very unfortunate, but they are not sufficient. So let us consider how we let us see how do we prove that thing. So consider this input and output states as we have done a little while ago, like this, except the last one. This one we are changing a bit. So we are changing here like this. Okay. So beta 0, 0 minus alpha 1, 1. Otherwise, it is the same as the earlier one, actually. Where, of course, alpha is greater than beta is greater than 0, and alpha square plus beta square is equal to 1. Now you see Nelson's criteria is satisfied for each pair. First observation, there is nothing to actually prove. But if you want, let me say a few words, a few lines on these things. For the B rather. So consider the concurrence, measure of concurrence actually. And you take a suitable probability distribution P, which sends this P comma 1 minus P when P is between 0 to half. Okay, for P is equal to half, in any case it is equal, concurrence is. So there is nothing actually. So in this case, you see that if you can calculate the concurrence, it will be of the form rho of psi comma P had the input states, the concurrence will be mod of 1 minus 2P. And for output states, the concurrence will be 2 into alpha beta into mod of 1 minus 2P. And clearly, because alpha and beta is less than 1, actually this thing is smaller than this guy. Okay. Now, the third condition, distinguishability conditions. But that is easy actually, because these two sets are actually distinguishable both locally and globally. So there is nothing much to prove here also. So if you want, you can see the paper of Walgett, Hardy, and Vitral. I should have given the references. It came in physical review letters in 2000. It's called the local distinguishability of multipartite orthogonal quantum states. So using the result, I can say that these two things are distinguishable locally as well as globally. Okay. Now, so what we are getting, the condition A, condition B, condition C, all three are satisfied. Now, the thing is, can we do a transformation? Well, LOCC transformations are a little bit difficult always, but I know one very famous result by Andreas Winter, X Dunbar, and quite other people, which tells the following, that which proves the following, that this LOCC is a subset set of all separable transformations. Okay, so if you can prove that there is no separable transformation which does this transformation, that psi1 goes to phi1 and psi2 goes to phi2, then we are true, because then there cannot be any LOCC either. Okay, so let us assume that there is a separable transformation. Separable transformation means some kind of a channel which actually where the cross operators are of the form tensor product kind of form. Okay, and which sends which does this nice trick that psi1 goes to phi1, psi2 goes to phi2. And because it's a channel, then it should also have satisfied that the dual of this channel has to be unital. So so this AK dagger AK, BK dagger BK has to be equal to identity. So what if I apply this channel on psi I? By this psi I, I'm just using a shorthand, that is the ket psi I, bra psi I. Okay, the projection onto the psi I, or the state psi I actually. Then you see it will be of this form, summation of K, AK tensor BK, psi I, AK dagger tensor BK. So what we get from the right hand side? It will be, the right hand side will be equal to phi I. So if I take psi1, I should get some kind of, I should get the output will be of the form of phi1, and when I get psi2, I will get the output will be of the form phi2. Now that means if I do a little bit of work, some linear algebra here, then I should get this AK tensor BK acting upon phi1 should be some complex object mu of K1 times phi1, and AK tensor BK times psi2 should be some mu of K2 times phi2, because the output of the right hand side should be equal to phi I, right? So it should be, which is a pure state. So the left hand side I can write it as term by term, I can break it. Now from here what we get? You see, I have two possibilities. The first possibility is that this coefficients, so mu of K1 and mu of K2, these two coefficients are non-zeros. And in the second case, I can get that at least one of the coefficients is equal to 0. Okay. So this is a very, very bizarre situation right now. Hello, am I online? Hello? Hello, guys. Hello.
You are perfectly audible. You can continue.
Oh, okay. So I just
slide is just unshared. You can share it again.
Now I can put the file.
Yeah.
Oh, can you see it now? Can you see it?
Yeah. It is visible. Huh?
Okay, fine. Okay, now so let us see now. So as I said that there are two possibilities, that this mu K1 and mu K2, both of them are non-zero, or the second possibility, one of them is equal to 0. Both of them cannot be equal to 0, because then the output will be equal to 0. That's not the thing, right? So so at least one of them can be equal to 0. So let us consider the first possibility when both of them are non-zeros. So if I do a little bit of addition here, because after all I know what is psi1. Psi1 is equal to the 1 by square root of 2, 0, 0 plus 1, 1. And psi2 is 1 by square root of 2, 0, 0 minus 1, 1. So I can just add them together, and I would get the following nice thing, that AK tensor BK 0, 0, which will be equal to square root of 2 into this condition, that mu K1 alpha plus mu K2 beta 0, 0 plus mu K1 beta minus mu K2 alpha 1. Now, you see this side, left hand side is a pure state. It's a separable state also, because I'm just doing nothing other than a separable operation. AK tensor BK acting upon 0, 0. So this is a separable thing. Now the right hand side must be also a separable object. How do I check that thing whether it is separable or not? Well, I can take the partial, it's just qubit system, so I can take the partial transpose and do whatever I want to do, and I can find out that this ratio, that mu k1 divided by mu k2, this can be either minus beta by alpha or alpha by beta. Similarly, I can get this ratio will come up when you calculate the whole thing. And in the same spirit, if I can just subtract that thing and I can take the 1, 1, then I get something like this in the right hand side. And this will give me the same ratio as either beta by alpha or minus alpha by beta. See, the point is here is that if I get the choice minus beta by alpha, I am getting from the second equation, I am getting this side as beta by alpha. It cannot hold. Minus beta by alpha cannot be equal to beta by alpha. Or in the same spirit, when this first thing gives me alpha by beta, the second thing gives me minus of alpha by beta, which cannot hold again. So they both together cannot be true. That means both mu k1 and mu k2 cannot be non-zero. So next, I will show that both of them cannot be zero either. Because both of them cannot be zero either, because let us assume that said in the case that mu k1 is non-zero and mu k2 is equal to 0. Then I again come back to this original thing. I come here and then I try to simplify the values. Then I get this thing that AK tensor BK is equal to mu k1 and AK tensor BK psi 2 is equal to 0. Now if I just add and simplify, then what I get here, the left hand side, I will see the side, this here will be a product state, whereas the right hand side will give me an entangled state. If I just add, because this holds, because we have cleverly chosen this as 0, 0 plus 1 or 0, 0 minus 1, 1. So if I just add them together, I will get a product state. But the right hand side, thanks to our choice of alpha and beta and mu of k2 is equal to 0, the right hand side, the first one is equal to some non-zero multiple of phi 1, which is an entangled state, and then the second one is equal to 0. So the right hand side is an entangled state. So I cannot really have a state. I cannot really have an LOCC transformation which sends one set of state, this set of states, input states, to this set of output states. So what we have now found out is that this set of states is not sufficient. So in a nutshell, what we have worked is the following. We have given a set of necessary conditions. Unfortunately, we have not found out a set of substitute conditions, but that is okay. In many cases, in this LOCC conversions, we really have one-sided kind of results, but not the other-sided. And this gives us a nice way, an operationally interesting way, because so far what we know is that if we really want to do some kind of a communication protocol, then this LOCC in a bipartite situation, then the LOCC, these kind of protocols are easier to actually do. So in this situation, I cannot do the transformation from this state to another state. This is true. And the third thing is that, which I have not put any slide on it, that the idea is that this hierarchy, that the LOCC is a subset of separables, and all this thing holds also. We can give some examples, but I don't want to go in that direction anymore. And there we are also continuing working on this project. So something we expect to get some more results. By the way, the paper which I have, the archive number which I have told, so that appear, that is going to appear a physical review here shortly. So that is it. And thank you all for your attention. I'm in time. I didn't take more than an hour. I have been funded by DST, so that I should also thank to them. So thank you all, and thank you all the organizers. And time for questions, maybe.
Yeah, thank you, Ritabrata. I
Okay.
think I don't see any question in the chat box, so we can go to the directly to the audience. They can ask question directly. They can unmute themselves. And
Okay, sure.
yeah, so organizer is writing that participants can also write their questions in the chat box. That will be easier to communicate it. Yeah, I agree. So whoever is
Right.
having questions can write
Let
in the
me
chat
see.
box. Yeah, there's no no questions so far.
What is trans? What is trans? I think.
Yeah, I think that will be for you, addressing to you, because there was another thank you. So I thought I was a bit confused whether for Professor Chaturvedi or for you. If you think it is for you, then
Oh,
you
I
can
see.
actually address this question.
No. I think it is. It's not to me.
Yeah, because
Probably.
at 12:11 there was a thank you, and then it was
Yeah.
at marginal time when you
Yeah.
started, right?
Yeah, exactly.
Yeah, any questions? If not, then maybe anyone can contact him for further discussions, questions, anything. And let me thank the speaker again. Ritabrata, thank you very much for your talk.
Thank you very much. Thank you for calling me also. Well, hope to see you again someday.
Yeah, sure. And then